All right, so we'll now, in the third part of cardiovascular, we'll talk about the electrical events that happens in heart. Now, why is this electrical event even important? Because this is the event, and because of these events actually, or the summation of these events actually, heart is able to contract all the time. So heart actually depolarizes, but the interesting thing is it doesn't take any help directly from nervous system. So obviously it is still connected to central nervous system and everything, but heart beats on its own. Okay, and although it is heavily regulated by autonomic nervous system, and the reason the heart can do this because it has a lot of gap junctions in them between the cells, and then it has its own intrinsic cardiac conduction system, which is, so the conduction means the conduction of the impulse of within the heart, that is done by a bunch of cells, group of cells, which is the autorhythmic cells, means they can rhythm on their own. So, and they help in initiation and then the distribution of the impulses, and then obviously coordination of depolarization and contraction. So again, remember depolarization, you learned this in action potential, that is the main reason why any impulse would actually even happen. So same thing applies here. So, firstly, action potential, obviously, where will it happen? We learned that heart has pacemaker cells, and they are responsible for doing the pace, the speed of the heart, the rhythmicity of the heart. Okay, they have unstable resting membrane potential. So first of all, there is three parts of this whole action potential of pacemaker cells of heart. Firstly, it starts with pacemaker potential. What is this pacemaker potential? This is a very slow, when the depolarization is really starting, very slow depolarization. Opens the sodium channel over here and closes the potassium channel, and slowly it gets towards this line. This is a baseline. But you will see that this is a autorhythmic, like it starts like this and goes down and goes up and goes down. So there is no as such flat line, it will not never be zero. So that means if it's zero, that means there is a problem in heart beating, right? So firstly, pacemaker potential, so slowly it's going towards the depolarization, sodium channels are opening. Then it slowly rises to depolarization, means action potential. The action potential begins after, again, this has a threshold value which is around here, it reaches the threshold, and then it goes into action potential, same as you have learned before. After it reaches action, the threshold, there is no nothing looking backward. And then all the depolarization here actually mainly happens, yes, there is sodium channel starts it, but it mainly happens due to calcium influx through calcium channels. Again, remember, calcium is also a positively charged ion, so that can also shoot up action potential, and this is more applicable for heart cells. So after the action potential, half-moon depolarization is at its peak, which is action potential. Then of course this next step will be repolarization, which means that the calcium channels will inactivate. And what will happen? So there is no entry of calcium channel, but the potassium channels will open, because like any other cell, heart cells also have more presence of potassium in them. Now potassium will start getting out, same as the action potential that happens in any other nervous cells. So this allows, when the potassium channels open, potassium efflux. Okay, and then the membrane voltage starts dropping and goes to negative voltage, so that it can get started with another pacemaker potential, another depolarization, another repolarization. So it's a cyclical manner. If you don't remember these steps of action potential, please go back and review this for 208. It is slightly different from what you have learned there, but the basic idea is still same. Okay, now the cardiac pacemaker self, it is carrying this action potential, but it does the whole rhythm, the whole intrinsic conduction system, like one whole rhythm basically, is conducted in 0.22 seconds. The whole impulse is passed within 0.22 seconds, every single impulse, right? So it starts from this node called SA node, the sinoatrial node. This is also called as the pacemaker of heart. I'm sure you've heard about, like, people get pacemaker in their heart, and that is because this is where the pacemaker is. If this node actually stops working properly, this is where the artificial pacemaker is actually given. But what does this do? Why it is so important? Because this depolarize, firstly, this actually generates the impulses. The depolarization actually first starts here, and it is the depolarization is much more faster than end of the rest of the myocardium. It generates the impulse which stays, which is approximately per minute. It can generate up to 75, which is called a sinus rhythm. If it is tempered by some external factor, like you are exercising, you're jumping around, you're running around too much, then this can go high, up to like approximately 100. Okay, so this is where the impulse form starts actually. Then it starts spreading across the whole heart. Why is it important? Because this impulse is required for the heart's contraction. This impulse is going to help the cardiac muscles to contract. Okay, so now from the sinoatrial node it is generated. Now it is time for it to spread around the heart. The second step, it will go here, which is the AV node, the atrioventricular node, the node between the atrium and the ventricle. Okay, now this is all happening in the right side, remember. Now here the what happens, it's basically the AV node is in the inferior interarterial septum, means basically between the between the septum of the two atria. And then here the impulse is slightly delayed, approximately 0.1 second, means it waits for 0.1 second, waits there for a little bit. The reason, because the fibers here are smaller in diameter and have fewer gap junctions, and that is okay. Why it is okay? Because this allows that the atrium is totally contracted, because the impulse have like spreaded across the whole atrium, and the atrium has totally contracted before the impulse goes into the ventricle. So it basically allows the impulse to spread around the entire atrium. Okay, and now it will be around here. So inherent rate is 50 per minute if there the SA node is somehow disturbed. So if there is some problem in the SA node, this rate can actually drop. The AV node function can drop. Then now from here it will get into this particular small little area called as the atrioventricular bundle. Okay, which is on the interventricular septum. So it is not on the atrium anymore, it's in the ventricle already. It's between the interventricular septum. All right, and only this is the electrical connection between the atria and the ventricle actually. So now it has passed into the ventricle. All right, and now from here it will now actually spread around more. So now you see this bundle has actually branched off into right and left. It has branched off into right and left, two different pathways, because it has to go into right and left segment, right? So now it will branch off and it will go into these subendocardial conducting network, which are the Purkinje fibers, which is on the ventricular like wall over here. So from the septum it goes into the entire wall of the ventricles on both direction, right and left. So what this does, this also takes the impulse towards the apex of the heart, towards the point of this heart. So now the whole impulse that is generated here is actually have spreaded around almost throughout the whole heart. The last step is actually, since the when I'm saying that the impulse have passed, that means it has been here in this Purkinje fibers, and this is called a subendocardial conducting network. This also means that the depolarization actually have all impulse means basically generated by the depolarization that has actually spreaded across the whole heart, starting from the atrium, now in the both the ventricles, right? So now this particular network of Purkinje fibers, so here it divides into the left and right. Now it is spreading in the Purkinje fibers, but the fiber is a little bit more elaborate on the left side of the heart. Now remember, I just told you before, the reason behind the left side itself has a thicker wall, because it has more, the mass is required more here, because it ejects the blood to the entire body. So therefore this particular fiber system is also a little more complex over here. Now, like we said before, the process of the whole SA node initiation to the complete contraction to the complete impulse of being carried away takes approximately 0.22 seconds. All right, so this is the how the whole heart is actually doing the rhythm. That's a basic mechanism, like you learned about the steps of the heart how the blood is actually flowing, and this is the background mechanism by which that blood flow can be done so efficiently. Okay, this is the background autorhythmic mechanism that is making the blood flow so efficiently. Now, if there is any problem, what would happen? For example, we can see arrhythmia. So that means simply irregular heart rhythm. The atrium and the ventricular contraction is not regulated properly, uncoordinated. This fibrillation means rapid irregular contraction. Heart becomes it's less useful for, basically it cannot pump blood very well. Okay, which means that the blood circulation can cease and brain will not get enough blood. Means might result in brain death also. Treatment is nothing but defibrillation. Somehow this defibrillation has to happen, the irregular contraction has to be stopped. Quickly about the action potential, little bit more in the contractile muscle cells. So contractile muscle fibers make up the bulk of the heart and responsible for the pumping action. So like here, the action potential that was generated by the pacemaker cells. So this is a constant action potential that is generated by the cardiac pacemaker cells. Here, the contractile muscle fibers are also responsible for this pumping action, right? So these muscle fibers also undergo action potential. What are the steps of that? Firstly depolarization, and then the platophase is slightly different from what you learned about the skeletal muscle fibers. So what happens here? Firstly, you will see that there's a lot of sodium influx, so that goes on a real super high real fast spike in the sodium influx, and then it opens up in a positive feedback cycle. The sodium actually keeps going inside, generating the action potential. Then it reaches the platophase where calcium influx now happens, because calcium moves a little bit slower. Now plateau means that is like it's going to stay in a flat state for a really long time, and this whole generation of action potential by these contractile cardiac muscle cells are itself is a little bit slow. And of course after this plateau phase it will drop down to the negative potential again, like we saw in the pacemaker cell. So these are contractile muscle fibers that are also responsible for the pumping action, the muscle fiber itself. So they also undergoing the steps of action potential. Now, what is the difference between the skeletal muscle fiber contraction and this contractile muscle fiber contraction? AP in the skeletal muscle lasts for really small time, 1 to 2 seconds, but in cardiac muscle cell it can last up to 200 milliseconds. Contraction in the skeletal muscle lasts for 15 to 100 milliseconds. In cardiac contraction it lasts over 200 milliseconds. Benefit of longer AP and contraction is basically because it can give us sustained contraction, right, to efficient that the entire blood has been ejected, and longer refractory period also prevents the tetanus condition, means getting the muscle getting stiff. Okay, now echocardiography. What is echocardiography? Echocardiography is a test that actually can measure the electrical currents measured by the heart. So this is a test. So whatever we learned about, like how can we measure it, this can be measured by the echocardiography. An echocardiogram therefore is basically the graphic that is being recorded. It is also called as ECG or EKG. Okay, now it is basically nothing but the composition of all the action potential, not one, all the action potential. It has a pattern, the heart has a pattern of this action potential as the action potential keeps going. Okay, and we actually typically take around 12 points for measuring the different points of our body that is used for measuring this action potentials from all over our body, and then we create a EKG or ECG graph actually with the help of these 12 data points. So that's how a normal EKG or ECG will look like. You will have a P wave, then a QRS wave, okay, this peak, QR is complex rather, and then from there it will have a T wave, right? So what does this mean? These are the three waves or complex, three main ones. So what does this mean? When it is at P wave, means it's the depolarization of the SA node or the atria. Okay, so remember we spoke about how the impulse is basically flowing from the atrium to the ventricle, again to the entire heart. So that's the impulse is flowing, but it starts from the atrium, right? So this simply means that here the atrium is depolarizing. Okay, the atrium is depolarizing from the SA node, right? And then it comes to the QRS complex. Here the ventricle is depolarizing. Now the impulse, when it has gone to the ventricle from here to here, now the ventricles will depolarize. Impulse have passed from the atrium to the ventricle. Now the ventricle has depolarized. Now when the ventricle is depolarizing, in the back the atrium is going back to its depolarized normal position again. So when we are in the QRS complex, the ventricle is depolarizing, but at the same time at the back the atrium is actually repolarizing. So now we are here in the ventricles depolarization. And now obviously again it will go into this peak where the ventricle also will have to go back into its repolarized state, right? So these are the three peaks. What are the intervals? P and R. P and R is a beginning of atrial excitation, which starts from the depolarization, and beginning of the ventricle excitation. So kind of in the middle of starting from the atrial excitation, where the depolarization is starting in the atrium, and then the peak of the ventricular excitement, which is the ventricular depolarization. So from here to here, one depolarization to one depolarization, from this depolarization to this depolarization, P to R. S and T, which is this one, so means the entire myocardium, entire ventricular myocardium is depolarized, means the entire ventricle is actually totally depolarized. Q to T, which is here to here, beginning through the ventricular depolarization, and then also here T is totally included here. So Q to T means the entire ventricular depolarization and repolarization. Okay, so PQR, P, QRS, QRS and T peak. P means the atrium is depolarizing. QRS, the ventricle is depolarizing. This part, at the same time at the back, the atrium is going back to its repolarized state, right? And the T peak means the ventricle is repolarization. If I am measuring from peak P to peak R, means it is the entire depolarization phase, starting from atrium excitement or depolarization to atrium excitement or atrium depolarization. S to T, from here to here, means the entire myocardium is depolarizing. So it's basically measurement of the whole depolarization. And Q to T means beginning of the depolarization in ventricles, and throughout we are also measuring the end of this, which is the ventricular repolarization. So from here to here, entire ventricular episode actually, QT. So again, P is the atrial depolarization. It is initiated in the SA node over here, causing that results in the P wave. Then it comes in here. So basically around here, not yet peaking. So here the atrium has already started repolarizing. When we reach this peak, the ventricle, it is in the impulse is already in the ventricle. Now the ventricle has starting to like depolarizing. At the peak it depolarizes, so QRS. At the same time the ventricle, the atrium has gone back to its repolarized state. So after this, now the ventricle is in depolarized state, right? In number 4, the ventricle depolarization is done, it's complete. Now it will get into the ventricle itself, will again go back to its repolarized state again. Okay, and then it starts after PQRS, and then it is done when we are at T basically. Then it is already, the ventricle is already in repolarized state, and when T is over, the ventricular repolarization is also over. This is a very, very important figure, and this will basically summarize you everything that we just learned. It summarizes together the whole depolarization repolarization event, as well as how can we measure that with EKG or ECG tracing. So patterns in or timing of ECG actually can tell us about disease condition in heart. For example, if we have a really enlarged R wave, so suppose this is really enlarged, really super big, that that means that what, this is the ventricle is depolarizing here, so it means that something is wrong with the ventricle, so enlarged ventricle. If you have a really big ST segment from here to here, what does this mean? Again, there is some form of ischemia, something is wrong in the ventricle again. If we have a prolonged QT interval, that means again QT means here to here, again means some form of ventricular arrhythmia. Okay, so this is a normal EKG. So we can see here like P, then this is Q. I mean this is Q, then R, S, and then T. So we can clearly measure out this thing. Again, let's see one other one. P, let me write it here. Q, R, S, and T. So it's more or less normal. We can see all of these peaks pretty clearly. Okay, this is called normal ECG trace or sinus rhythm. If you see a little bit abnormality in this, for example, here we can see here, let's see here, we can see an S, I'm sorry, Q, R, S, and T. But if you look in the area of P, the area of P, that is a little bit like it's kind of flat, so there are P waves are absent. So this kind of condition will call as the junctional rhythm. There's some problem. If we see this kind of, this actually means that this is second degree heart block. As a result, if you see here, there are way more P waves. Okay, there are two P waves than there are QRS. So there is QRS, this is the R peak and this is the T peak, but first of all there is some form of arrhythmia, but there are way more, like here we can see there is 2 P wave. Okay, this is not pretty normal, and then suddenly we again are seeing this is another 2 P waves coming. So basically there are more P, not necessarily it will happen all the time. For example, here there is one P wave, but again after finishing off this T, so this is P, Q, R, S, T, this is kind of generating a small P here, then a gap, again a P here, then QRS, and then this is the T again. So this is some kind of problem, and it is generating way more number of P's than the QRS complex itself. So this is called second degree heart block. Some kind of blockage is there, so that's why the rhythm is not normal. If you see this simply means ventricular fibrillation, means the entire activity is disorganized. There is no such proper pattern. So action potential is really random throughout the ventricle. It's chaotic, gross. So this can actually lead to acute heart attack. So this is a very like one should be aware if the, I mean, should be aware of this if this is happening to someone. Now atricular repolarization means what period of time in ECG? Atricular repolarization actually, it should be near, so whenever the ventricle is depolarizing at the same time, so when the ventricle is depolarizing, the atrium has already depolarized by that time. So when the, therefore the ventricular, when the ventricle is at depolarization, when this is depolarizing, then the atrium has already depolarized and it's in the repolarized mode. So this will be QRS. Number 8, ventricular repolarization occurs during this time and it is seen on an EKG. This I'm pretty sure you can figure out by looking at the graph. So work on this by yourself. All right. Next thing, we'll talk about cardiac cycle, heart sounds, stroke volumes, and then how autonomic nervous system actually plays role in this whole thing, and then the developmental aspect of heart. We'll talk that in the fourth part.